We're going to begin by talking about the fundamental counting principle, which we have studied before, and I have it here. The fundamental counting principle says if one event can happen in m ways and a second can happen in n ways, then the total number of ways for both to happen is m times n. Notice it's times here. We're looking for multiple events to happen. That's and rules, so we're multiplying. It says here, suppose 3 fair coins are tossed. Use the fundamental counting principle to find the total number of outcomes. So I would ask you to think about this, and this is what helps me to decide how to do this. I have 3 coins that are going to be tossed. This is a slot problem for me. In each of those slots, I got to figure out the number of possible outcomes. So 3 fair coins, 2 outcomes on each. So 2 in that slot, 2 in that slot, 2 in that slot. Fundamental counting principle says multiply those guys, and 2 to the 3rd power is 8. There are 8 possible outcomes. So the fundamental counting principle can give you that number. The tree diagram can show you the outcomes, right? This can get you the number, but a tree diagram is the way if you want to see them. This tree will have 3 stages since there are 3 coins to be flipped. At the first stage, of course, that first coin could either come out heads or tails. From each of those possibilities, the second coin could give a head or a tail, and you can see how that's building. Second coin still, a head or a tail. And then for each of these possible outcomes, the 2 previous, the third coin could also give a head or a tail, a head or a tail, a head or a tail. This tree diagram is already getting longer than I would want to have to do, so if I were doing many more than 3, I probably would not do a tree diagram. However, it is very useful if you want to see a listing of that sample space, because as you follow down the branches you can see all the possibilities for outcomes. I would remind you that you could add a 0.5 probability on each branch here, 0.5 for each of those, and then figure probabilities using your tree. There are 4 blood types, and they're listed here. Blood can also be Rh or positive or negative, so 2 different Rh factors, and blood donors can be classified as male or female by gender. How many different ways can a blood donation be labeled? Well, this is a perfect place for that fundamental counting principle, because we've got 1, 2, 3 categories of stuff, so that makes this a 3-slot problem. Blood type is the first slot, and there were 4 of them. Rh factor comes next, and you can either be positive or negative. Gender comes last, and you can either be positive or negative. So we're looking at 4 times 2 times 2. That's 16 possible labels. Good. Carrying on that same thought, suppose the digits 0, 1, 2, 3, and 4 are going to be used in a 5-digit ID card. If you allow repetition, that means the same number can be used more than once. So your 5-digit ID card is 5-slot problem. Each of these with repetition could be 5. And that's looking like 5 to the 5th, which I should probably know, but I don't. 3,125 possible ID cards if you allow for repetition. If you don't allow for repetition, you still have a 5-slot problem, but things change. The first digit, there are 5 choices for that. The second digit, since you can't have repetition, one of your possibilities is gone, so you're down to 4, then 3, then 2, then 1. And I'm wondering, I'm going to ask you to think about this. Can you think about the name of that kind of multiplication where each time you're going down by 1? Some of you will remember it. It's 5 factorial, and the notation for factorial is the exclamation point. And 5 times 4 is 20, 20 times 6 is 120, and 120 times 1 is 120. So with no repetition, only 120 cards. That changes things quite a lot when you limit the repetition factor. That last example problem uses, again, it's factorial multiplication. That last example illustrates what we call a permutation. And a permutation is an ordering or arrangement of objects, or digits in this case. And the permutation that we looked at in the previous example would be written this way. We had 5 objects. We were doing permutations of them chosen 5 at a time. We wanted to use all of them. Your calculator can do that for you. If you 5 and then math key down to the PRB menu, and you can see permutation is the second choice there. 5, choose 5. 120 possible arrangements. What happens when you don't use all the digits? Well, if the ID numbers were 3 digits instead of 5, still selecting from the 5 how many different ID tags could be printed. We'll give you a generic formula for this. It goes this way: NPR, where N is the number of objects, R is the number that you are selecting, the formula for permutations is this: it's n factorial over n minus r factorial. If you apply that to our ID card problem, we are wanting 5 digits chosen 3 at a time. And the formula, which is the way I learned to do this, I didn't have the calculator obviously when I learned, 5 factorial over n minus r, so that's 5 minus 3, 2 factorial. And if you think about the math involved here, 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2. A lot of canceling there. And we have 20 times 3, 60 cards if you limit the number of cards, or the number of digits, to 3. Your calculator can certainly do that for you. 5 P3 60. The formula is good, for at least for me. I like to think about where the numbers come from. So then the next question asks us to do a similar arrangement. How many different ways can a chairperson and an assistant be selected from a group of 7 members? Well, in this case, n is 7. That's the total number of objects that you have. R is 2. And the formula would say 7P2 is equal to 7 factorial over 7 minus 2, 5 factorial. You guys, this is why I say the formula is so handy. 5 factorial is 5, 4, 3, 2, 1. 7 factorial is 7 times 6 times 5 factorial. So basically, what you'd have to do in this problem is just multiply 7 times 6, and there are 42 different arrangements. And if you want to verify that on your calculator, of course, you're welcome to. Let's move on and carry it to the next level. Permutations are ordered groupings. Okay? A lot of times when you talk about permutations and combinations, you hear people use the word order. Permutations are about order. How many different ways could we select 2? Combinations are not about ordering or arrangement. Instead, combinations involve sets. Okay, the idea is the number of sets of n objects chosen are at a time. For example, suppose it says a committee of 5 is to be chosen from a group of 26. If the committee with students A, B, C, D, and E is chosen, is that different from the committee with these students, C, A, E, B, D? No, they're the same people. The order that you select them doesn't matter in a combination, okay? It's just the ones that you have selected that matter, not the order that they're taken. The formula for finding NCR, that is combinations of n objects chosen R ways, is very similar. It's based on permutations, So n factorial over n minus r factorial. But then you also have to divide out the repetition, and that happens by dividing again by r factorial. If you think about that particular problem up there, 5 chosen from 26, 26C5 would equal 26 factorial over 26 minus 5, 21 factorial, times r was 5 factorial. The math of that, well, 26 factorial, 26, 25, 24, 23, 22, and then anything from 21 is canceled. We also have a 5 factorial on the bottom to worry about. So here's where you divide out repetition. And there we go. Let's see. There's a 24 right there. Here's a 5. And just using the formula, you can find that relatively quickly. It's certainly not as quick in this problem as with your calculator, but 26 times 5 times 23 times 22 is 65,780 combinations or sets of people from 26. That's a lot. 65,780 sets of 5 people chosen from a group of 26. I want to just check my work. Can't stand not knowing if I did it right. So this time we want NCR, and that's the third option here. And our R was 5. Oh, look at that, 65,780. So yeah, permutations, combinations. How many ways can a set of 3 Christmas presents be selected from 10? By now this is old hat for us. We are doing 10, and it's a set. That's the key word. So it's a combination, and we're choosing 3 presents. Well, the formula would say 10 factorial over 7 factorial times 3 factorial. That would be 10 times 9 times 8, and then the rest 7 factorial would be gone. Now we got to divide by 3 times 2, 3 factorial, so that's a 3, that's a 4, and we're talking 30 times 4, 120 different ways. 10, choose 3, 120. Batting 1,000. That's it for today. Get out there and try the U-Try, please, and we'll see you in school tomorrow.